Question 7 from the calorimetry module checkpoint is a pretty challenging question. So we've got two different things we have to calculate here. So we've got this trimethylamine, which is burned in a bomb calorimeter, and the temperature of that calorimeter increases by 4.39 degrees Celsius. There's two things going on here. And what a bomb calorimeter is basically we've got kind of like this beaker of water. We've got a regular calorimeter. So here's our water. And then inside of it, we have our bomb calorimeter. So here would be the bomb part of that bomb calorimeter, and then here's the water. That's the other half of that calorimeter. So the combustion reaction takes place in here, and then it heats up this bomb calorimeter, right? It heats this up, but then it also releases some of that heat to the water as well. So because of that, we have two different calculations we have to do for this reaction, because we're heating up the bomb and we're heating up the water of this bomb calorimeter. So both components, both the bomb and the water of that bomb calorimeter. So first things first, right? The bomb, they tell us the bomb has a heat capacity, and this is important as well. And then the water, here's how much water. We know the heat capacity of that water, the specific heat of that water, the density of that water. So for the first part, we have to calculate the energy required to heat up the bomb and the water of the calorimeter. So as you can see from the heat capacity of the bomb calorimeter, it's just joules per degree Celsius. There's no mass there because this value is for the entire bomb calorimeter. So it's already including the mass. This is just for the entire unit itself. So that equation is Q equals C delta T, where C is our heat capacity of this calorimeter, the bomb calorimeter. So Q for this, well, they tell us that the heat capacity is 864 joules per degree Celsius, and this goes through a 4.39 degree Celsius temperature change. Now we can calculate for the water as well, and this would be Q equals MC of S delta T. So this Q, well, my water got 835 milliliters, which is 835 grams of water. We know the specific heat of water is 4.18 joules per gram times degrees Celsius. And the temperature change would be the same because the whole calorimeter goes through a 4.39 degrees Celsius temperature change. So we multiply both of those together and we can get our total temperature change for this. Just give myself some more room to work here. If I multiply all of these together, for the bomb, we're going to see that we are going to absorb approximately 3.79 times 10 to the 3 joules. And then for the water is going to absorb about 1.53 times 10 to the 4 joules. So we can add those all together. What the bomb absorbs, what the water of the calorimeter absorbs, to see the whole reaction is going to release about 1.91 times 10 to the 4 joules. So that's how much heat was produced by this combustion. I would say 1.91 e to the 4 joules. I would go with 3 significant figures because everything here looks like it would be 3 significant figures, right? Temperature, our heat capacity, our volume and mass of the water. Step 2, what is the experimental heat of combustion in kJ, in kilojoules per mole? So that's part 1, right? Part 2, we have to find this energy in terms of kilojoules per mole. So if you thought to yourself in the first part, well, there's some numbers I didn't really use. We're going to use those numbers now because we basically found the energy we need to convert that energy now and just from energy into energy per mole of trimethylamine that was in the reaction. So if we go and look up trimethylamine, right, trimethylamine has a molar mass of something like 59.11 grams per mole. So, all right, we've got 0.483 grams of trimethylamine, and we know 59.11 grams for every 1 mole of trimethylamine. That gives us about 8.17 times 10 to the minus 3 moles of the trimethylamine. So now we want to find kilojoules per mole. Well, right now I've got joules. So here's our energy, 1.91 times 10 to the 4 joules. We want to do a unit conversion to get this into kilojoules, right? We know for every 1,000 joules, there's 1 kilojoule. So the total energy in kilojoules is about 19.1 kilojoules of energy released when I have 8.17 times 10 to the minus 3 moles in the reaction. The last step, we're looking for energy per mole. So I've got energy, going to divide that by the 8.17 times 10 to the minus 3 moles that are in the reaction, because you'll notice that'll give us the correct units, kilojoules per mole, to see that this reaction has approximately 2.34 times 10 to the 3 kilojoules per mole for the heat of this reaction. 2.34 E3 kilojoules per mole. And as you can see from the midterm exam, this question is quite a bit harder than something I would have given you on the midterm exam, but it's good to work through a harder question because that would make the question on the exam feel a little bit easier. That being said, right, half of the question is certainly fair game. Certainly expected to do a Q equals MC delta T type calculation. And then the second step really isn't that too much more work because you're just taking that energy that we found and then converting that into energy per mole, which means we need to take what we had in the reaction and turn it into how many moles we have in the reaction.